So, okay. So, up to this we have seen, right, x to 1 and this thing. So, as just to all of you I have to tell one or two things. Look, actually this course, before proceeding to this, that so many computations are there, right. We all are human being. By chance if you find that all this calculation I hope I have made correct, but there is a possibility that calculator pressing and this that I may also commit some mistake in numerical values, because you are not sitting in front of me. That is why earlier also one or two places I have made some corrections, right. For example, instead of EP upon ES I wrote VP upon VS. Had it been in the classroom, immediately you should have corrected me, right. Similarly, multiplied that a square multiplied, it should have been division, that corrected also. Similarly, all these calculations, because later you will see many more calculations, right. So, if you particularly when you come load flow, then economic load dispatch and fault studies, right. So, if you find anything that calculation error or anything or any suggestion, you please send me mail, I will appreciate that, right, because huge your what you call computations are involved here, right. And anywhere if you see any error or anything or writing error or anything, please mail me such that I can rectify myself, right. So, now ZB your ZB line, that is the line base voltage, we computed it was 113.43 square upon 100, that is 128.66 ohm, right. And X line is equal to X line ohm upon ZB line, this is per unit. X line means X line per unit value, I did not write per unit, understandable. It is 60 upon 128.66 is equal to 0.466 pu per unit. Now, motor side, now same thing you can use equation your what you call equation 16, that old values and new values. So, previously all I have explained. So, all these things now you can make it very easily, right. So, I am writing directly, you try. So, XM1 ohmic value is 0.2 into 30 square upon 40, because first you have to convert it on its own your ohmic value in its own rating, that is own base values, right. So, for motor 1 base MVA was base kV was 30 and base MVA was the rated base voltage of the motor was 30 kV and MVA rated MVA 40. So, it is kV square upon MVA, that is on its motor this value always gives on its base your base value of motor rating, right. So, 0.20 into 30 square upon 40, that is 4.5 ohm, that is the ohmic values, but Z base we know 10.89 ohm, therefore, 4.5 upon ZB, that is 0.413 per unit. Similarly, other two you can easily calculate, these two directly you can calculate using equation 16, right. So, xm to nu is equal to 0.2 into 100 upon 30 into 30 upon 33 whole square, whatever it is, it comes 0.551 per unit. Similarly, for motor 3 you calculate same using equation 16, you will become 0.826 per unit, right. Once this is done, then you draw the per unit diagram, right. That means, this one, this is that single line diagram, that is a schematic diagram of all these things given, and this is your per unit diagram, right. So, generator, this is the generator, reactance was 0.15 per unit. So, it is given. Then transformer convert T1 also converted to a common base, whatever you have done, it was J 0.0683 per unit. Then this is the line, it is J 0.466 per unit, right. And then this is transformer T2, it is also both transformers they are same, that same rating, same reactance, right. So, J 0.0683 per unit, and 3 motors, they have all are in parallel, right. So, motor 1 J 0.413, motor 2 J 0.551 and motor 3 J 0.826, and complete the diagram. Only thing is, throughout the calculations, all this calculation I did not use J again and again, it will become clumsy putting J everywhere, rather you make as it is, and after that in the circuit diagram you put J, because from the using this voltage is given, motor terminal voltage, but everything is given. So, accordingly you may have to calculate current and the other thing that we will see during fall studies, right. But this is that. After that, in the diagram we have put all the J values, right. Next is that example 5, right. So, this is actually that this is small one, right, that 3 single phase transformer are given with their nameplate ratings, right. If you see any transformer, nameplate ratings are there, everything will get from there, right. Determine the reactance diagram when it is star star and star delta connections, picking the voltage and power basis for the 3 phase bank. That means, you have 3 single phase transformer, you are connecting them, one is 3 phase star star, another 3 phase star delta. So, you have to find out that your what you call picking the voltage and power base for the 3 phase bank, right. So, what we will do in per unit, whether it is star star or star delta, right, just see the transformer ratings are given, they are single phase, this single phase rating is 1000 kVA each, that is your 1 MVA, and voltage is 12.66 upon 66 kV for the single phase, this data for single phase, and leakage reactance is given 0.10 per unit, right, and it is your what you call and leakage, and in this case this XM is not motor, it is your magnetizing reactance, it is 50 pu is given, right. So, what you have to do is you have to see that even it is if you take per unit for single phase or per unit for 3 phase, you will find they are same, right. But this is for single phase per unit, it is given, it is magnetizing reactance is given 50 pu, right. Now, when you consider this for a single phase, so kV base 1 12.66 kV and kV base 2 66, because primary side it is 12.66, the secondary side is 66 kV, right, and MVA base 1000 kVA, that means it is 1 MVA 1000 upon 1000, right. So, ZB1 that is it is kV square B1 upon MVA base, that is 12.66 square upon 1, that is 160.27 ohm, right, when you are considering as a single phase, right. Similarly, that ZB2 is equal to kV square B2 upon MVA base, that is 66 square upon 1, that is 4356 ohm, right. So, this is actually actual reactance referred to the primary R, that x1 is equal to 0.1 into 160.27, that is 16.027 ohmic values, right, because this 0.1 was given, the leakage reactance here it is given, right, it was given XL, we are writing here as a x1 referred to primary, right. Similarly, XM is 50 into 160.27, 8013.5 ohm, right. Now, this transformer you are converting to star star or star delta. So, let us consider now the 3 phase interconnection of 3 single phase transformers. Now, if we connect the primaries in star, secondaries can be star or delta, because it is given star star or star delta, right, and they assume MVA 3 phase will and kVA base line to line, because for single phase rating was 1 MVA each single phase, now 3 single phase connected. So, MVA base 3 phase will be 3 into 1, that is 3, right, and kV base line to line, it was single phase 12.66 say one side. So, it will be multiplied by root 3, earlier also in one example we have seen, right. So, root 3 into 12.66 kV, right. Therefore, ZB1 is kV square base line to line by MVA base 3 phase, that is root 3 into 12.66 square upon 3, that is 160.27 ohm. Therefore, x1 will be original, earlier we got x1 is 16.027 ohm and xm is 8013.5 ohm. Therefore, x1 will be your 16.07 upon 027 upon 160.27 is equal to 0.1 per unit. Similarly, xm will be your 8013.5 upon 160.27, that is 50 per unit. Therefore, that means whether it is a single phase or 3 phase, these per unit values remain same, right. Therefore, your reactance diagram of star star and star delta connection is shown in this figure. note that reactant angle delta star or delta delta will also be same, right. So, this is your magnetizing shown in parallel J50, right. Rm is not considered in this example, just to show you, that is all, and this is your J.10 and this is other side, and showing a direction of the current I1 here, I2 here. This is voltage V1 and this is voltage V2 on the secondary side, right. So, just to show you. After this, you will, after this per unit system, other interesting thing you later you will find the method of voltage control, right. So, now for example 6 also you have to find out the per unit diagram. Here one generator is there, I will come to the data first. It is a if you think it is a 1, 2, 3, that will have something like a 3 bus problem, right. So, this is generator 1, this is generator 2 and load is here, it is load, right. This is transformer T1, this is transformer T2, and 1 to 2 line impedance is 4 plus J16 ohm, and 1 to 3 it is 2 plus J8 ohm, half of this, actually half of this we have taken for easy calculations, and this 2 to 3 is 2 plus J8 ohm, right, and this is load is given here. So, generator 1, this generator 1 is 50 MVA 12.2 kV and its reactance is given 0.10 per unit. Generator 2, that means this one 20 MVA 13.8 kV and its reactance is 0.10 per unit, that is Xg2, right. Therefore, this T1 transformer 1 is rating is 80 MVA, that means this one 12.2 primary side and 132 kV the other side, right. So, low voltage side is 12.2 kV and this generator also 12.2 kV and other side is 132 kV, that is line side, and transformer T1 reactance is 0.10 per unit. Transformer T2, this one is 40 MVA, but is 13.8 kV and 132 kV, that is the your high voltage side, right, and this thing your Xt22 is equal to 0.10 per unit, right. So, this whenever we load is 50 MVA, 0.8 lagging power factor and operating at 124 kV, that means this voltage of this bus 3 is actually 124 kV, right, and whenever transformer is given 30, here it is given where transformer 1 12.2 132 kV, that is this is the low voltage side, this side, and when you are going to generator 2 it is written 13.8 132 kV, actually this side is 13.2 and this side actually one low voltage side is always the generator side, right, although but it will be given like that only, right. So, it is actually this side low voltage side, the terminal voltage of generator 13.8 and 132 kV is the this side, this way it will be given. So, there should not be any confusion, and this is the sample power system diagram, right. And load is I told you 15 MVA and 0.8 for lagging, but operating at 124 kV, although line is 132, but due to the load and other thing voltage has say fallen to 124 kV, right. So, base kV in the transmission line we assume nothing has been mentioned here. So, we will assume 100 kV, right, we will assume say 100 kV. Just this arbitrarily we have to, instead of 132 or something I have taken 100 kV, such that all transformation will be easier for you, right. Whatever your base voltage you say, whatever answer you get in per unit, when you will convert it to real unit, at that time you will see the same thing is coming, right. I have taken here 100 kV, when you will solve this problem you take base voltage is 130 kV and solve it, right, whatever per unit values you get, but if you try to convert into the real quantities you will find the same values. And base kV in the generator circuit then 100 into 12.2 by 132, so 9.24 kV. This 100 kV intentionally I have made it for transmission line, such that I can show you all the transformation, right. So, it is 100 and but this one actually 12 this transformer actually it is 12.2 by 132. So, line side will be generator 1 will be base voltage will be 100 into 12.2 upon 132. So, 9.24 kV, right. So, it will go down. Similarly, in the generator side G2 will be 100 into 13.8 by 132. So, it will be 10.45 kV, right. So, all transformation you have to make on the common base. Now, for G1 you apply equation 16, right. So, equation 16 we are writing here, that suppose this one, there it was written x new is equal to x old something, but for in general that x g 1 new is equal to x g 1 old into MVA base new upon MVA base old into kb square base old upon kb square base new. You assume that MVA base new is equal to MVA base is equal to 100, right. So, that you assume 100. Now, MVA base old is equal to rated MVA of G 1. What I want to mean, whenever you will take old MVA or old kV means it is the rated voltage of the generator or transformer or motor, right, and old MVA means it is the rating of the generator, transformer, MVA rating of the generator, transformer or motor. These are always your old values, right. So, there should not be any confusion, right. Therefore, MVA base old, that is why I am writing MVA base old is equal to rated MVA of G 1 is equal to, it is given, data is given, it is 50 MVA, and KVA base old, that is 12.2 kV. This is also generator terminal voltage, that is also given here 12.2. So, any rated value, I mean rated kV and MVA, all old values means the rated, your old base means it is your what you call, these are all the old base, right, and new one is whatever you have assumed. So, this is your kV base old, that is 12.2 kV. Therefore, and your kV base new whatever you have computed, right, that kV base new for the generator 1 is 9.24 kV and for generator 2 10.45 kV, right. That means that kV base new, now I am rewriting this for your understanding only, 9.24 kV and xg1 old is equal to xg1 is equal to 0.10 per unit. xg1 old means whatever reactance of the generator is given, that is old value. Now, xg1 new is equal to, applying this formula, applying this equation 16, this is actually equation 16, right. So, if you put it, it will be 0.1 into 100 by 50 into whatever data you substitute here, you will get 0.3486 per unit. Once again I tell you that all this calculation I am making it, if I see calculator facing error always may be there, but I will request you make it of your own, right, all this calculation. If you find any error, you just send me the mail, that is all, right. So, I will such that I can rectify myself, right. So, similarly for G2, xg2 new is equal to, using this formula you will get 0.8719 pu, right, and for transformer T1 xt1 new is equal to, same way you calculate using the same formula, it will give 0.2179 per unit. Similarly, for transformer T2 x2 it will be 0.33 per unit. So, this intentionally I have taken this such that in one problem all sort of conversion to per unit can be shown, right, because these calculations are okay, but in the later stage you will see huge computation for all these things, right, for other topics. So, base impedance of the transmission line, we have taken 100 kV your base voltage and base MVA 100. So, ZB line is 100 square upon 100, that is 100 ohm, right. Now, Z12 line 12 its impedance was given 4 plus J16 ohm, that is Z12 pu Z12 ohmic value by ZB impedance of the line your base value of the line, right, line impedance. So, 4 plus J16 upon 100. So, it comes 0.04 plus J.16 per unit, and Z13 per unit is equal to Z23 per unit, because both are same, both line have the same impedance, is equal to 2 plus J8 upon 100, that is 0.02 plus J 0.08 per unit, right. Now, load specified is given, it is given that power, it is given 0.8 power factor lagging, right. So, that is why 500 0.8 plus J 0.6, right. Listen one thing, if lagging power factor is given, right, for the load, that means load actually is load means it is consuming power, right, it is consuming power from the source, right. So, whenever load is lagging power factor means it will be 0.8 plus J 0.6, right. So, I suggest that do not take it minus, then it will be a mistake, because load consume power. So, convention is that load always consume power, and generator it actually injects power into the line, right. So, it will be 4 plus J 30 MVA, as it is 4 plus J30 in bracket, we are putting MVA, otherwise this 40 actually megawatt and 30 actually megabar, but together, so it is MVA, right. Now, these things are there, load actually nothing is said that whether it is series or parallel, right. I mean it is a load, but whether it is loads are series in parallel, nothing is said. So, I will take series combination of resistance and reactance, right, and parallel combination also can be given, but partly I will show you, but other you do it, right. So, using equation 11, that when you go back to the equation 11, I do not know where it has gone, equation 11 is far away from here now, right, which pages, right. Let me see if I get it, otherwise directly you can go back, right. Just hold on, if I find it here, I will see that. No, it had mixed up actually, it does not matter. So, use equation 11, So, Z star load, that is conjugate, is ohmic value, it is based your base voltage, that load voltage was given that 124 kV, in the data it was given 124 kV. So, it is 124 square divided by 4 plus J30, sorry 40 plus J30, that is 307.52 angle 36.87 degree ohm, that is Z impedance of this thing is conjugate, this is conjugate, right. So, Z conjugate of load is 307.52 angle minus 36.87 degree ohm, right. So, this is your Z conjugate, right. Now, this is his impedance ohm, right. Now, this per unit value, that Z star, that is conjugate per unit value, that is Z conjugate this ohm divided by base impedance of the line, ZB line, right. So, it was 100 ohm for the base impedance. So, 307.52 angle minus 36.87 degree, right. So, that is 2.46 plus J 1.84 per unit, right. It was Z conjugate here. Now, both if you take conjugate on both side again, right. So, it will be Z load per unit and this angle will become plus, right. Instead of minus it will be positive, right. That is why it is 2.46 plus J 1.845. So, conjugate is taken actually on both sides, that is why it is this one. Therefore, R series is 2.46 per unit, this is the resistance part, and X series is 1.845 per unit. Only parallel connection of resistance and reactance will be, R parallel will be 124 square upon 40, right, and that is your resistive part, load was 40 plus J30, right. That means your 40 megawatt is the base value. So, that is why 124 square upon 40, 384.4 ohm, and R parallel per unit is 380.44, but 100 ohm is the base impedance. So, 3.844 per unit, right. Similarly, X parallel, that 30 megavar is coming for the 40 plus J30 load, 30 megavar. So, that is why 124 square upon 30. So, 512.5 ohm. So, X parallel per unit will be 5.125 per unit. Up to this I have shown, rest for parallel part you will do it, right. But I will show you only the series connection, right, only the series connection. So, this is the diagram, this is the per unit reactance diagram, right. So, this is generator 1 J 0.3486 per unit, and this is your what you call transformer J 0.2179, then 3 lines are there 0.04 plus J 0.16, and this 2 reactance for these 2 line impedance for these 2 lines also shown. This is also transformer your T2 J 0.33, and this is generator 2 reactance, and after that this load 2.46 the resistive part, and this is your series reactance part, this is the load, and diagrams this connection is complete, right. Now, this one I have made it parallel one, I have showed you only this part, parallel one I have showed you only this part. So, you can compute, you can make this diagram, right. So, this is your per unit diagram. This is actually required for fault studies, another thing later we will see. So, how this thing, but if you instead of 100 kV base voltage, if you choose some other base voltage also, these parameters will be different, because things will be different, but ultimately when you solve the network and you will convert them all the values, voltage, current, power and impedance in the real values, you will find the same values, right. So, from this I think this will be the last example for you, right. After that we will go to the new thing. So, there is a this is a parallel circuits are there, T1, T2, T3, T4, 4 transformers are there, line 220 kV line, and this is line 2 is 132 kV line, this is 132 kV line, right. And this transformer rating also generator is 90 MVA and 13.8 kV, Xg is given, T1 transformer T1 50 MVA, 13.8 by 220 kV, transformer reactance is given. Then transformer T2 also reactance is given, and this is another one motor is here, another load connected here also, right. Transformer T2 50 MVA 220 upon 11 kV, 10% reactance is given. Transformer T3 50 MVA 13.8 by 132 kV, 10% is given, and motor 80 MVA 10.45 kV, reactant 10% is given, load 57 MVA, this is the load is also there, 7 MVA 0.8 power factor lagging at 10.45 kV, because generator motor is at 10.45 kV, right. Line 1 impedance is 50, reactance is 50 ohm, this line 1, line 2 this one 70 ohm, and you have to find out that your per unit impedance diagram, right. So, this problem will quickly will make it, right, and this one will make it quickly. So, the generator rated voltage is given as the base voltage at bus 1, right. So, this fixes the voltage basis for other buses in accordance to the transformer turns ratio. So, generator actually 13.8 kV. So, we have taken base voltage of this VB1 13.8 kV. So, naturally VB2 will be 13.8 220 upon 13.8. So, 220 kV, that means this line voltage also will be base voltage will be 220 kV, right. Now, for base voltage of the high voltage side of transformer T2 is VB3 will be 220 kV, that means this side base voltage for the transformer will be 220 kV, because line base voltage is 220 kV. Therefore, and on its low voltage side it will be 220 into 11 by 220. So, 11 kV side 11 kV. So, this side will be 11 kV base voltage, right. Now, similarly, VB5 is equal to VB6 13.8 into 132 by 13%. So, 132 kV, that means your this side and this side, and this side base voltage, that is VB5, VB6, this side 132 kV. I marked 1, 2, 3, 4, 5, 6, right, 6 such buses it has been marked, right. Therefore, VB5, V6 this thing, this base voltage is chosen such that base voltage for other things automatically will be transferred, right. So, directly. So, base MVA we have chosen 100, but generator base different. So, you have to convert to their that is your new base. So, 90 MVA is the generator rating, that is their old base MVA, and this is the new 100 MVA, 100 is the new base MVA. So, 0.18 into 100 by 19, 0.2 per unit. All transformers are 50 MVA rating and 0.10 per unit. So, 0.1 into 100 by 50, because 100 MVA is the base. So, 0.20 per unit. Now, using equation 16, this is the same that new and old relationship using equation 16, right. So, XM old per unit 0.2 per unit, MVA base old 80 KVA base old 10.45 kV, MVA base new is 100, KVA base new is equal to 11 kV. All these things are given before. So, you one by one you will put it, and you will get XM new per unit 0.2256 per unit. Then base impedance for lines 2, 3, 5, 6, all you calculate VB2 square upon MVA base, you will get 484 ohm. Similarly, for 5 to 6, VB5 square by MVA base 132 square by 100, 174.24 ohm. Line 1 base per unit impedance it is 50 upon 484, 0.1033 per unit. Line 2 it was 70 upon 174, because 70 ohm was given, 174.24, 0.4017 per unit, right. So, this all line and generator computed. Now, the load is at 0.8 power factor lagging. So, it is 15.7 MVA. So, SL 3 phase is 57 angle 36.87 degree MVA. This we have seen before, and load impedance is given by VLL square upon S conjugate L 3 phase, right, that is 10.45 square 57 angle minus 36.87 degree. This also we have seen. Therefore, ZL will be 1.532 plus J 1.1495 ohmic values, right. So, this is actually ohmic values, right. Now, base impedance of the load is, it actually we have got 11 kV on the other side. So, 11 it is given 11. So, 11 square upon 100, that is 1.21 ohm, right, all data are given. Therefore, ZL per unit, this whole thing you divide by 1.21, you will get 1.266 plus J 0.95 per unit, right. So, this one I made little bit faster, because all examples we have shown, right. Therefore, per unit equivalent circuit diagram is shown in figure 20, that means this diagram, right. This is generator, then you have two parallel lines, transformer, then line, then again transformer 0.2, 0.1033, 0.02 again this, and for other line this is J 0.2, because all transformer per unit was same. So, T1, T2, T3, T4 they have after conversion point this thing, but this line it is 0.1033 and this is J 0.4017, and motor and load they are in parallel. So, motor impede this side XM 0.2256, this is motor, and this load resistive part is also there 1.266 and J 0.95. So, this is that per unit diagram. So, for this your per unit some 7 different type of problems I have shown you, right. And next time we will take that method of voltage control, and you will find that your what you call your tap changing transformer, right, off and on load, right, at the same time different type of method of voltage control, you will find things are interesting. So, thank you.